Today we are going to talk about hypothesis testing. We're gonna first describe what would be the descriptive statistics, and we're gonna prepare for inference statistics using normal distribution or sampling distribution. And after that, we're gonna talk about estimation and hypothesis testing. So all the things you have learned so far are used for this hypothesis testing. This is one of the key elements of this course. Also, this will be used for your final project. I mean, and also for the regression analysis that we're gonna learn in chapter 11 and 12. So we learned that estimation is something like based on some samples, we are trying to estimate the true parameter, population parameter, right? Using sample, that is like an estimation, right? Example was, okay, mean gas price in the New York State or fraction of defective parts. So how hypothesis testing, I mean, these are the things we learned in previous chapter, right? Hypothesis testing is, we are actually testing, okay, how confident are you? For example, I mean, you can say, based on some sample I have, mean gas price in New York is $2.5 or whatever dollar per gallon. Um, but you want to test against it. So for example, is the mean gas price higher than $4? This is like something you are testing. Or is the defective rate lower than 1%? You want to actually get some statistical result instead of just average, you know. So hypothesis testing is a unnatural way of inference. However, it is similar to the way of our thinking commonly used in research. So in research, let's say the effect of some medicine A on the treatment, then we want to know how the effects of the medicine on some disease. So instead of saying, okay, this is working, you want to know how confident your result would be. So those are the things are used for hypothesis testing. So for example, this is one more question and try to answer this. So criminal procedure is similar to statistical inference. For example, statistician is a prosecutor. So unknown parameter is whether the defendant is guilty or not. So sample is evidence. So if there is no evidence, what would be the legal decision? So if there is no evidence, then they'll be innocent because there is no evidence at all to support that. So it is somehow unfair inference. The defendant is considered not guilty until proven guilty. It's actually the same thing in statistics. Until you find a statistically significant result, it's not actually having an effect. So, I mean, I'm gonna discuss more that in the later part. The prosecutor has the burden of proof. So statistical hypothesis testing is similarly unfair. So presume that a hypothesis is true. So, and you have the burden of proof if hypothesis is wrong. So based on the data you have or sample you have, you need to prove that those are actually working. So if you cannot find enough evidence or, I mean, you don't find any statistically significant result, then you do not reject it. But if you find it, reject it. So I'm gonna come back this issue. So let me discuss more about that. So the null hypothesis is not rejected until you have enough evidence against it. So we usually denote it by H naught. And alternative hypothesis is accepted only when enough evidence against null hypothesis. So we usually say we do not accept, we actually fail to reject. We actually cannot reject based on the result. So we usually say, okay, for example, this is underneath over here. So result of a test can be rejected or not rejected based on the inference. So let me go with some result. For example, the null hypothesis is dependent is not guilty, but the alternative might be the dependent is guilty. So it's always opposite. Do not reject our null hypothesis. It does not mean that the dependent is innocent. Well, we don't have enough sample or the data to support that. So a weak conclusion is cannot say H not, which is our alternative hypothesis is wrong. So reject null hypothesis means there is sufficient evidence of a crime. So evidence again in our data set is like a sample. So a strong conclusion is H not is wrong. Our null hypothesis is wrong is our conclusion. So similar structure. So paradigm shift, helicocentrism, the sun rotates around the earth or the earth rotates around the sun. So this is null hypothesis and this is alternative. So our null hypothesis was believed until too many contradictions were shown. So these were based on some results or supporting evidence. And then we reject the null hypothesis. So the conservative decision making is the null hypothesis is existing system is better. Alternative is a new system is better. So new system is chosen only when it's proven better. So using some kinds of data set, right? I mean, when you're actually gonna work at the company later after graduation, they might say, okay, which should be better? I mean, should we launch a new product or not? And we might want to test the product out to some customers, sample customer, and say, okay, the new product is better than the previous one, and based on that, we decide to use the new products. So that those kinds of things are actually used for in the real life. So Super Bowl coin toss is another kind of example. So think of a Super Bowl coin toss. So x1 equal 1 equal tail, heads, and the x equal 0 is tail. So this is like a binary, right? We learned in chapter 5, right? So P is the probability of x equal 1. So we leave the coin as a fair, though we don't have any evidence. So our null hypothesis is, okay, probability of head is 50%, or the alternative is not, it's not fair. So basically, you should be able to convert our present assumption or the null hypothesis in mathematics. For example, if this is a fair, then probability of x equal 1 or head should be 50%, otherwise it's not. So we actually want to test it. So suppose you draw the coin for 10 times. Which result is more supportive for the null hypothesis? So first answer is you get 8 heads and 2 tails, and 6 heads and 4 tails. The answer would be actually D, right? So 6 heads and 4 tails would be better. It's supportive, right? Because it's more close to 50%. This is like 80% and 20%. So the closer the ratio of heads is to 50%, the more supportive for the null hypothesis. So I call an event extreme if it's unlikely to happen. So for example, when you flip a coin 10 times, but all the 10s are heads, or all the 10s are tails. So those are extreme outcomes. So definition of a p-value, it's gonna be used a lot from now on, so keep those in mind. So the probability of more extreme events than the observation when the null hypothesis is true. So when the null hypothesis is true, then we are looking for probability of more extreme events. For example, probability of, or the 10 coins are heads, that would be 1 over 1024, right? Or 1 over 2 to the 10th power. That would be your extreme probability. That is actually p-value, probability of more extreme events than the observation when the null hypothesis is true. So you get 8 heads and 2 tails, more extreme events. So binary distribution with n equal 10 and p equal 5. So I'll go back to our chapter 5, and it will give you a probability equal 10.94%. So the probability that when you flip it 10 times, but you're gonna get 8 or more heads is actually 10.94%. So those are actually our probability. So it's gonna be 10 or more, including it can be 8, 9, or 10, right? So you are adding all the probability, it's gonna be 10.94. Those are actually concept of a p-value. So you get 6 heads or 4 tails, 6 or more, include 6, 7, 8, 9, 10, which already include that. This is a subset of this, right? So it's gonna be 75.2%. 0.39. So it's going to be a huge probability, right? So based on that, so probability that you're going to have a 5 head or 6 head, 7, 8, 9, 10, you just plot them and a p-value distribution. So it looks like a normal, right? So as you can see, those are the probabilities. So p-value measure how supportive the data are for the null. So high p-value means the data are comparable with the null, right? But low p-value is the data are unlikely with the null. So it's not likely. So low p-value means you are more likely to reject the null hypothesis. So if a p-value is 0, the null is certainly wrong. But if p-value is very close to 0, then your null hypothesis is more likely to be rejected. So if a p-value is not 0%, the null can be true, right? So null can be true means you fail to reject. So we may be so unlucky to have 9 heads even if the coin is fair, but it would be very unlikely. The probability is very low. So the null hypothesis is rejected if a p-value is too small. We define too small by preset of alpha. So we learned alpha, which is a significance level in previous chapter, right? Chapter 8. So alpha is used for here. For example, alpha equal 5% means what? What? So the significance level would be 95%, right? This is a a confidence level was 95%. If a significance level is 5%. So when you make a decision whether you reject or not, you're gonna make the decision based on the significance level alpha and p-value. For example, if a p-value is greater than alpha, you do not reject, and then p-value is less than alpha, you reject. This one is so important. I cannot emphasize enough. Okay, so for example, you get the p-value equal previously in this example, you get 10.94. For example, and you decide to choose a significance level of 10%. And since 10.94 is higher than 10%, so you do not reject. Or sometimes you say you fail to reject, or you do not reject the null hypothesis that the coin is fair. So you do not reject that. So these are most commonly used alphas. So, but on the other hand, let's say your p-value was 0.04. Then what? The alpha based on the 5% level, this is 4% is less than 5%. So you reject the null hypothesis and accept the null alternative. So this is another example. A murder took place at noon. Actually midnight last night, and I just made an assumption for illustration. A major suspect said he returned home before 12. There are many witnesses who saw him returning home. So we want to test whether our null hypothesis is he returned home at noon. Actually midnight, and alternative is he did not. So let X be the witnesses time of the return. The witness time is random, so due to inaccurate memory. So I just made up. So we would like to test if the mean of X is 12 a.m. So our alternative is this, and our null hypothesis equals 0, alternative is not. So we will make a decision based on X bar, that is a mean of X, So X bar is called test statistic. So to listen for the difference between that. So X bar and null hypothesis. First thing is a random error. Because of some error associated with that, so even if our null hypothesis is true, it might not be. Or other reason might be the null hypothesis is not simply true. So if the random error is too unlikely, then we conclude that null is not true. Therefore, a natural way to make a decision is the reject the null hypothesis if the deviation of X bar from null is too large, because the large errors are unlikely to happen. So this is a true population parameter, mu, and X bar is from sample. So the extreme outcomes are p-value, as I said, is unlikely, right? But X bar close to mean would be more likely, right? So for example, if this X bar is close somewhere around here, then you say you cannot reject, or you do not reject, you fail to reject, right? The null hypothesis. But on the other hand, something is like a very extreme values, right? Or p-value is so small, then you are likely to reject your null hypothesis. So based on the location of X bar, you can reject or cannot reject. So you have to define how unlikely X bar under null hypothesis. We will use a distribution X bar to measure the unlikely. I mean, previously, we in a couple chapters ago, we learned about the normal distribution, right? I think in chapter 6, and we were able to find the z-score associated with that. I mean, this is a basically similar idea. You want to find the probability associated with the extreme outcomes. So based on that, you can make a decision. For example, T statistic, again, we went over T statistic in the end of last chapter. So that was used when the true parameter, the population variance or population standard deviation is unknown, right? And also sample size is small. We are trying to use a T statistic, but it's gonna converge to normal distribution when you have enough sample size. Since we don't know the true variance or standard deviation of a population parameter, so we are trying to use the T statistics. So mu naught is the value assumed under null hypothesis, and if null is true, then it's approximately standard normal. T-stat is a standardized measure of deviation from null hypothesis. So as we did in Z-score, so based on something and based on your mean and standard deviation, and you are able to find some probability associated with that, that would be your p-value. So we did those in our previous chapter, and it was actually in the chapter actually 6 as well. So 5 as well. So those are the thing. So p-value is the probability of more extreme deviation than observed. So if a p-value is too small, then deviation is large, so very unlikely. So we are more likely to reject. Again, you compare the p-value with the alpha, right? Significance level. So if a p-value is large, the deviation is small. So our decision rule will be the reject the null hypothesis, right? If a p-value is too small. So conventional rule would be 1%, 5%, and 10%. In the research, in medical research and other many research, we are likely to use 1% and 5%. These are most commonly used rule. So for example, significance level of alpha. So the threshold that we decide the p-value is not small, usually again this range in the probability of a more extreme outcome if a null hypothesis is true was that. So as I discussed before, this were the decision rule. Suppose this is a case. So before you that looking at that, try to looking at this literature. So try to find the T statistic without looking at the answer. This would be good practice for the midterm and for your own understanding. So X bar was what, 5. Mu 0 was 0, right? Our null hypothesis. And then S was 5, and then actually S was 20, and N equal 100. Plug in, you would get 2.5. So graphically, how it's working is, similar to Z-score, right? Similar to Z-score. So, I show you in previous lecture that how to look at the T distribution table. It's at the end of your textbook, right? So similar to Z-score, so you are actually looking for this. So this one is 2.5, and this is normalized, so 0. So you want to find the probability associated with that, right? For example, T equal this would be, so probably associated with this. For example, this is a probability because we are actually looking at, I'm gonna come back this one later, next chapter, but two-sided, we are looking at two-sided test. That means because it doesn't matter whether the time based on our 12 a.m., whether it's greater than or smaller than, it doesn't matter. Whether it's smaller or greater, the side doesn't matter. What we matter is whether it's different than the midnight. So 2.5 was actually it's positive number. So what you need to do is you should plug in here as well, 2.5, negative 2.5, and find this error. So so that this is a probability associated with this would be, for example, based on the T-stat table, whatever number, I'm just made up the number, say, or actually, let me show you how to find. So let me, in this case, we don't have to use T distribution table because with the enough sample, we can make the assumption with the central limit theorem, the t distribution would be about the normal distribution. So we're gonna just use the normal distribution table. This table, the PDF file was posted on the Blackboard. So take a look at that. So we had a 2.5, which is a 0.9938. So this is a 2.5 and 0 z-score. So that would be 0.9938. I explain super detail in chapter 6. So if you don't understand how to look at this table, go back to that, okay? So 2.5, the numbers I got was actually 0.938. This one was actually probability. So I'm gonna just mark in the blue. Look, this was a probability that this area on the left, right? That means this one, this is a probability of what? This is actually, this was a probability of z actually less than 2.5 was 0.9938. In other words, a probability of z greater than 2.5, which is the probability we are looking for over here, right? That would be 1 minus 0.9938. So that would be something like 0.0062, something like that. So that would be the probability over here, these very extreme values. Well, we know this is symmetric. So if this is 0.0062, this would be same. It's going to be 0.0062, right? So for example, I mean, you can actually take a look at that. So let's go back to here. And another way of doing it is, I mean, if you don't forget about symmetric, as you can see, probability that z less than 2.5 would be like that. So 0.0062, right? So this was 0.0062, 0.0062. So you have two sides. So p-value is what? P-value would be basically, I'm gonna just write over here. So p-value would be the probability of extreme value. Again, we are working on two-sided table because it doesn't matter the direction, whether it can be smaller than or greater than. It doesn't matter. What we actually matter is whether they are the same and different or not based on this the midnight. So we are looking for this area and this area. So basically, this would be a summation of probability that z less than negative 2.5 plus probability of z greater than 2.5. Well, we know this one, these two are equal, right? So in other words, it's going to be 2 times probability because they are symmetric is equal. I explained in chapter 6 in detail. So z greater than 2.5, or we know this is 0.0062, so 2 times 0.0062, that would be your answer. So no, 2 times 0.0062, so it's going to be 0.0124, something like that. So 1.4%. So based on that, what can you conclude? So it's about 1.24%. So based on that, what can you conclude? So this is actually our decision rule was if this was alpha, right? If alpha was greater than I know actually this is not alpha, this is a p-value, but based on our comparison between this and alpha, so this is a p-value, so we can compare to the p-value such that I'm gonna just delete everything over here. So if our p-value is greater than alpha, whatever threshold we are setting, usually it's gonna be 1% and 5% or 10%. This one is what? 1.24%, right? So it's gonna be actually less than 5%, right? So you say, okay, your conclusion would be you reject the null hypothesis at 5% level or alpha equal 5% level. So that is your conclusion. But say we decide to choose alpha equal 1%. In this case, what 1.24% is greater than 1%, our alpha, right? So you say we cannot reject or cannot reject the null at alpha equal 1% level. This is your conclusion. So based on the selection of alpha, sometimes you can reject, you cannot reject. So this would be a wonderful example. This can be potentially your exam question. So please go back and study until you understand. If you have any question, always let me know, okay? So we got t equal 2.5 and example was our null hypothesis was this is equal, mu equal 0 and x bar equal 5, which means the average within this memory is 5 minutes wrong, right? So since it's positive, that means it's gonna be positively wrong. So it's gonna be 12:05, and if it's -5, it's gonna be 11:55, something like that. So p-value is the probability that average memory is wrong by more than 5 times. So this was our outcome, and based on that, it's gonna be actually so. We are able to convert that. I already showed this on the board, right? So and we found this is actually t equal 2.5. So we are actually find the probability again graphically. This was extreme values. So you are looking for value over here and here. That was extreme value. So so I explained more detail in the on the board. So the probability of less than that is this, and greater than that is also this. So you multiply this. That was your outcome. So since 1.24 is less than this, so you reject at one, you cannot, actually 1.24 is higher than that. You cannot reject the null hypothesis, but you can reject the null hypothesis at 5% or 10% level, right? So p-value is less than alpha means you can reject. So depending on the selection of alpha, the outcome would be different. So we have this one. So as you can see, this is not equal to 0. That is alternative hypothesis. So this is called the two-sided test, as I mentioned on the board. But later in the following chapter, we're gonna learn about what if this is greater than or less than that. That would be one-sided test. The result would be slightly different based on our t-stat. I will come back to that. So let's say alpha equal 5%, and these are our result. What is the t-statistics? So please try to work with that. The answer is x bar minus mu 0 over this, so 1.5. So what is the p-value? Please spend some time to get this. The answer would be this based on this region. So you come back to the normal distribution table and find the z less than negative 1.5. It's this, and greater than this, so it's 1 minus of this. So summation is like that. In one-sided test, for your information, we're gonna learn later, we are not going to talk about these two results. On the other hand, we're gonna either keep this one or keep this one based on our direction. For example, if this is, we keep this one, then this is our result, which should be 0.066. So we reject the null hypothesis at 10%, but we cannot reject at 5% for one-sided. But since we are dealing with the two-sided, we got to summate them up. So this is higher than 10%. So what is the result of the test? So based on that, we cannot reject because of what? This is actually higher than 5%, so we cannot reject. So again, this was two-sided, but next course, next week we're gonna talk about this on one-sided, but idea is almost similar, but only difference would be in the alternative hypothesis, right? This is not equal, so it can be either negative side or positive side. So it's going to be two-sided. On the other hand, if this direction is like that or like that, it's going to be one-sided, okay? So if null hypothesis is rejected, if p-value is less than alpha, that was our the decision rule, right? If as alpha increase, the higher probability to reject null, right? So for example, alpha equal 1% and 10%, more likely to reject the null hypothesis. Still trade-off, still the testing is in favor of null hypothesis. So If you claim a research hypothesis, put it as null hypothesis. If accepted as a low alpha, your claim is strong. For example, if you reject the null hypothesis at 1% level, you are very strong than rejecting at 10% level. So rejecting at the smaller alpha would give you more stronger claim. So if your research hypothesis is alternative, for example, the smaller p-value, the stronger your claim is. There are three ways of doing that. So far, we talk about p-value. If a p-value is less than the t, less than the alpha, then you reject. This is actually most convenient way, and I like it most. So most of the time in research, they're gonna use it first, but I'm gonna teach you the other two ways you can do. Practically, they are the same, exactly same information, but using different method. For example, p-value approach. We already talked about that. This decision rule, we already talked about that. So let's look at the t-statistic approach. So usually t-stat is presented together with the p-value in most statistical software. That is true. When you learn the regression, you're gonna see both p-value and t-statistics. In fact, you can calculate the p-value from t-statistic. So does not need alpha either, this case. So for example, so remember, p-value was just 2 times probability of z greater than this, right? Because of the symmetric, this is just summation of the extreme values. Suppose that your significance level is alpha, so you do not reject null hypothesis if p-value is greater than alpha, right? And we know, we learned this in our previous chapter, that probability of z greater than z, alpha over 2 is like that, right? So we therefore do not reject if this is the case. So for example, the intuition of this is like that. Okay. So let's draw a table. So using a p-value would be something like, okay, you have this t-stat, whatever you're getting, let's say 2.5 in previous example, and this was your p-value, which the summation of this was 1.2 something, 4%, something like that, right? That was p-value. If it's greater than something alpha, then you cannot reject. It's less than alpha, you cannot reject, right? You can reject. So reject. This is cannot reject. So that's what's using p-value. Second method is basically t-distribution. The idea is that, okay, the 95% confidence interval corresponding t-value would be t equal basically 1.96, right? So that is what we have learned before. So in other words, this is basically, okay, idea is, okay, the area between here to here is, I want it to be 95%. Then this would be 1.96, and this would be negative 1.96, right? So you remember how we get that? Previously we already discussed this a lot. So if we don't know how to get that, make sure you are going back to the previous slide, okay? And then 97, and then okay, let me just, and then 99% would be something like here, it's going to be here to here would be 99%, right? So 99%, it would be 2.58, negative 2.58, and then 90% would be something like, okay, it would be, I want it to be 90%, it would be 1.64 and negative 1.64, right? These are some of our values, z-score or t-values. So based on that, what you can make decision is, okay, if the t-stat we are getting, t-stat was what? T-stat was basically x bar minus mu over s over square root of n, right? That was what we learned previously. If the t-stat is between this interval, then we cannot reject. But it's outside, we can reject. For example, let's say t equal to, let's just, actually we did over here, so 2.5. Let's do this example. So we were able to get the p-value based on t equal 2.5 in this example, but let's say I just want to use the second method, then which is t equal 2.5, then okay, 2.5 is what? Somewhere over here outside of this range. So absolute value is somewhere here, 2.5, or here, 2.5. Both of them have outside range, right? So since the t-value you're getting from here is outside of this 95% of the T-score range or T-score range, 1.96. So it's out of the range, so you reject. So here you reject as well. On the other hand, the 2.5 is slightly inside of range. So since this is inside of range, 2.5 is between 2.5a and negative 2.5a. In other words, you cannot reject. This is a decision rule. So that is the whole point of the second idea. So okay, let me go back to the screen. Okay. So for example, if t is between this one, z alpha over 2 and negative z alpha over 2, if z is 5%, then it's going to be negative 1.96 and 1.96. And if this is 1%, it's going to be 2.58 and 2.58, right? I mean, we discussed that and I show over here. So if t is greater than or this, reject at 5% level. And by the way, I forgot to explain. So this means you cannot reject at 1% level, alpha equal 1% level, or 99% confidence interval. So this one reject at 5% level, because the 5% is the difference, it's alpha, because this is significance, I mean the confidence level, so significance level is 5%, this is reject at 10% level. So this is how you do that. Okay, okay. Okay. So these are the most commonly used number. I already explained that. So most of the time for your homework and exam, you're gonna use around this range. Suppose that you have a t-stat of negative 2.1. So please try to do all this on your own, right? So I will just leave you the answer, okay? Alpha equal 1%, and this is like that. So negative 2.1 is lie inside the inside, but outside of this. So you reject at 5%, 10%, not in 1%. So graphically, I'm gonna show in blue. So negative 2.4 is outside of here. Negative 2.1 is negative 2.1. On the other end, it's inside negative 2.1. So you cannot reject at 1%, can reject at 5 and 10%. So those were the whole idea of this. So that would be, yeah, answer is reject at 5 and or 10, not 1%. So p-value is like that. So you get the exactly same answer based on that. It doesn't matter which method you're using, t-statistic approach or p-value, but I mean, p-value would be much easier. So another approach would be critical value approach. So simple idea is do not reject the null hypothesis is x bar is close enough to mu. So reject the null if it's too far from mu. So there must be threshold m such that like that. So the idea is there must be threshold m such that we do not reject if x bar is between this range or reject if this is not the range. I mean, this is actually used quite a lot in the research. So I'm gonna teach you what that means. So before that, let's just define this as a, critical value upper bound, which is over here. And this is a CL is a lower bound. So how is it working? Is like that. Okay, so previously we learned that the x bar, the critical value would be something like mu m plus minus n, right? This was like from previous chapter. So based on that, graphically, this is like that. Okay, this is mu plus m, and this is mu minus n. So visually speaking, this is if x bar is inside of this range interval, then we cannot reject. But if x bar is outside of this range or here, then you reject. So this is reject and not reject. So how do we get the m based on that? So that is actually support over here. So previous chapter we learned that for 95%, in the confidence interval, we said this is what? We said it's m equal basically z alpha over 2 times s over square root of n, right? This is the standard of error. This is the significance level. For 95%, it's going to be 1.96 times s over square root of n. That was outcome. So it should, since it's a positive, so it's positive. For negative m, it should be negative. So basically, it's going to be mu plus minus z alpha over 2 times s over square root of n, where this is equal m, right? So we learned this in detail previous chapter. So okay, so that was the idea. So the rejection region referred to outside of interval. Let's say this is your upper bound and lower bound. So as I just explained, so you reject if this is outside, and otherwise you cannot reject. So for example, it's not rejected the alpha when the t is inside of this range, which is equivalent. This is from the second part, and I just explained you this one, right? Which is equivalent to this. Why? Because t is what? T is a mu. This was x bar minus mu. So let me explain over here. So I mean that was basically the idea exactly. So let me show you the math, just for someone who are interested more. So that would be negative z over alpha over 2. So this is actually z alpha over 2. So that was the previous case. T was what? X bar minus mu over s over square root of n. So this was z alpha over 2, and this is negative z alpha over 2. So you multiply this both sides. So it's going to be x bar minus mu and z alpha over 2 times s over square root of n. So this would be negative z alpha over 2 times s over square root of n. Next thing is you add mu both sides, which should be just add mu both sides. It would be like that, mu plus mu minus. That is how you get that mathematically. Okay, so the CL lower bound would be this, actually just C upper bound would be that. So reject is, I mean, if this is outside of this interval range, you reject. If it's inside, then you cannot reject. For example, alpha 1, 5, 10% respected z value is this from previous chapter. Very similar to the confidence interval. Given x bar, construct an interval for mu, and critical value given h naught, construct interval for this. This is the main difference, okay? So let's look at some examples. So x bar is 5, s equal 20, n equal 100, and alpha equal 10%. So corresponding z value would be z alpha over 2, which is z 0.05 is 1.64. So critical value would be like that, mu naught plus minus like that. So mu naught equal 0 in our case. So z alpha, which is 1.64 times s equal 20 over square root of n. So this is this range. So critical value is like that. So if z is x bar is outside of this, so we reject them at 10%. For example, yeah, this is like okay. The one thing I want to note that this is before standardization. So previously in t statistic and p score and p value thing, we actually think this is 0 and this was a z value or t value, right? This was after you standardize it, right? Standardize. So we learned this in chapter 6 and a previous chapter as well. So this one and this one slightly different. So this one is based on actual value, but this is you standardize it. So that is the main difference. What this is telling us is, okay, I'm gonna just remove this part. And okay, they said this one x bar is based on this mu, which is 0 plus 3.28 and negative 3.28. Again, this one is not t value or z score. This is actual value, margin of error. So this one and this one not equal. So do not make any confusion, okay? So since 5 x bar is outside of this range, So you reject at 10%. Similarly, I mean, you would reject at 5%, but you cannot reject at 1%. You might want to try out why. So similarly, at alpha equal 1%, please try to find that. Your answer would be actually here. Critical value of L equal 5 point, here the C would be your answer. Make sure you try out and why this is the case. So only change comparing to the previous case would be here, G alpha over 2 equal 2.58. It used to be 1.64. So if you replace and plug in, you'd get plus minus 5.16. So 5 is inside of this range, so you cannot reject. That is the case, and based on that, C is 5.16, 3.92, 3.28. So based on that, you reject. So you cannot reject over here. Can reject, can reject. So for alpha equal 5%, 10%, you can reject, but you cannot reject. This is consistent to our first case and the second case, because or should give you the same, but with a different method. So make sure you guys try to get the same thing. I already revealed the answer, but you please try alpha equal 5% and 1% on your own, and whether you get the same thing. So the critical values get wider as alpha decrease, right? So when the standard deviation increase, data is getting noisy, so more chance of getting large error. So if sigma, which is a part of the margin of error here, is sigma increase, or the standard deviation increase, this is from sample, and this whole margin of error would increase. On the other hand, if alpha decrease, this one increase, so margin of error increase. And when sample size increase, holding this one constant, everything, the standard error decrease as a result, margin of error decrease. So given same confidence level, you'd have a smaller interval, which is good because it's much more precise. I explained the similar concept in more detail in previous chapters, so please go back to and listen to the lecture if you are still confused, or let me know if you have any questions. So when the sample size decrease, so that means it's going to be standard error increase, so more marginal error. So etc. etc. And what is your conclusion? So your conclusion, what? Reject when so based on that, let's say your critical value is 10. So for x bar equal 3 and 5, so if we draw it is something like that. Oops. Oh, okay. Okay. So and it's a negative 3.92. That plus minus that. So 5 is outside of range, right? So you reject, but x bar equal 3, you cannot reject because inside of this critical value. So that was the idea. So this is another types of example. I-beam is a standardized steel beam used in construction. Suppose that height must be 80. So it must be 80. So you want to know whether the height is about here. So when you're actually working at a company, you might want to test it out using some samples. So X be the height of this is like a real kinds of example, real life example. You can apply anything, right? X is the height of the I-beam, and a construction company want to test whether this is 80 or not. So they have 400 samples. So they found, oh, X bar is 81 actually, and standard deviation of 10. Can you reject or not? So based on only looking at X bar 81, I mean, you might not sure. Okay, I mean, it's different by 1, but can you reject statistically significant or not? So you need to test it out. So T statistic would give you 2. So based on that, what is your conclusion? You can use method 1, 2, 3. So let's use whatever method you like. So 1.64 is 10%, 1.96 is 5%, and 2.58 is 1%. So based on the second method we talk about, for example, this one, this is the range is negative 1.96 to 1.96. So this is slightly outside of the range. So you can reject the null hypothesis at 5%. That means you can also reject at 10% level naturally. You don't have to say you reject null hypothesis at 5% and 10% because rejecting at 5% implying rejecting at 10% as well. So based on that, however, you cannot reject at a 1% level. So I use the second method, but you can use first method or third method as well. So whichever is fine. So you can reject at 5 and 10%. So 5% imply 10%. So technically you don't have to say, but null hypothesis is rejected at 10 and 5, not 1% by statistical approach. How about p-value approach? So based on t equal 2, can you find the p-value? Please work with it, but p-value is what? Actually, answer is between 1% and 5%. The p-value using this one is actually 4.5, right? Percent. So you reject at 5 and 10% and cannot reject 1%. Of course, the result will be the same. It doesn't matter which method you're using, 1 through 3, or give you the same answer. And then using critical value, you get because you are so what is the critical value? So the answer is, so upper bound is 79 and the lower bound is, upper bound is 80. 0.98, lower bound is 79.02. So you actually can reject at 5%, right? Because this 81 is slightly outside of this 95% range, so you can reject, but you cannot reject at a 1% level. So nice thing about p-value is based on p-value, you can say 5%, 10%, 1% easily because you can only compare alpha to the p-value. So this is super easy. I mean, nice thing about it is, okay, 4.55 is greater than 1%, so you cannot reject that 1%, but less than 5%, less than 10%, so you can reject easy. But critical value, every time you want to do 5%, 10%, and 1%, you got to do this again. So that is cumbersome. So we reject null hypothesis when x bar is less than that and that. So this is a rejection rule. So suppose you don't want to reject. This is actually a good question. Please take your time and answer. I will leave it to answer right now, right? We don't want to reject, so decrease alpha to 1% because that means it's going to be much wider. So that is more likely to be this one. The 81 would be inside of this range, right? Interval. So as the wider the critical value, you are more likely not to reject. So lower alpha means the critical value would be higher, range would be higher, so you're less likely to reject. So suppose that you are changing to 82 and you have a 400 sample size and center data, etc. So what is your conclusion? Please spend at least 5 to 10 minutes to work on it. I will leave you the answer. So you get t stat equal that and p value equal like that. So reject 10 and 5%. So I mean, those are basically same repeated question. That's why I'm a little bit going faster, but it doesn't mean that you can go faster. Please work with it. Make sure you get the same result as I show you here. If you have any question, always reach out to me. Or if you have a question, or also you can look at the previous chapter, like last chapter and chapter 6, if you are still confused with the t-stat and z-value kind of stuff, or cannot look at the table, z-score table. So please spend some time on this, okay? We have the same data over here. So when this one is 80, so you not reject, but this one you not reject. Even the same observation, the result can be different because the null hypothesis is different. So based on your null hypothesis, sometimes you reject and sometimes you reject. So that was the main idea. Okay. Okay. So this is exactly same, similar. I mean, same question, but it's basically binary variable. So only difference is binary. So I'm just testing whether p equals 75 or not. So based on this one, you can actually recover this null hypothesis. Practice this is so good. So 75% of people who got the flu shot do not cut a cord. So your probability, your assumption is to be 0.75. So you're testing against that. So variance of this is just p times 1 minus p. We learned this in chapter 5. Okay, based on that, what is the t statistics? So answer is just plug in that value. Finally, you to get this. So so based on this t-stat, we know z 0.05 is this one. This is 10% level. So what can you tell? So this t-stat, the absolute value of this is actually higher than that. So you actually reject at 10% level. This is not 5%, it should be 10% because this is z alpha over 2. So this is a 0.05 means it should be 10%, okay? So Z is used for this, and T is outside of this range, so you reject. So for this one, you reject, but 1% you don't reject. So that is for p-value, same thing. Using p-value first method, 2% is higher than 1%, so you cannot reject at 1%. On the other hand, so you can reject at 5% and 10% because this is lower than 5 or 10%. So again, this, as you can see, this is much easier. So I prefer p-value method, but other things, I mean, critical value is also intuitive. So I sometimes use and recommend. So based on critical value, and we know this is how the standard deviation is working, so you can find the critical value. So 0.7 is outside of this 10% range, right? So since 0.7 is outside of this range, so you reject at 10%. Similarly, you reject at 5%, but you cannot reject at 1% level. For example, what is a critical value? I mean, this is actually good exercise for you. So please spend some time on this. So your upper bound and lower bound would be 69 and 80% respectively. So 0.7 is actually inside of this range. On the other hand, you cannot reject the null hypothesis and 1% level. So I already revealed the answer for this, but please spend some time on this on your own, whether you can recover exactly same thing or not. Okay, and also work on with your homework, and please let me know. I'll raise if you have any question. Okay, thank you so much and have a great day. Bye.